Today we are going to learn about quantum algorithms transforming AI efficiency. We will explore how quantum algorithms like Grover's and Shor's are revolutionizing AI by offering significant computational speedups. By the end of this video, you'll understand how these algorithms optimize AI models and decrease processing times. Welcome to our exploration of quantum algorithms transforming AI efficiency. Quantum algorithms are computational processes that leverage the principles of quantum mechanics to solve problems more efficiently than classical algorithms. Unlike classical algorithms, which operate on binary zeros and ones, quantum algorithms exploit the phenomena of superposition and entanglement, allowing them to process a vast number of possibilities simultaneously. This capability has significant implications for artificial intelligence, potentially transforming the efficiency of AI models. In this video, we will delve into two pivotal quantum algorithms, Grover's and Shor's, and see how they promise to revolutionize AI by dramatically speeding up processing times. Grover's algorithm is a quantum algorithm that provides a quadratic speedup for unstructured search problems. Imagine searching through a database with n entries. A classical algorithm would require O(n) operations, but Grover's algorithm can accomplish the task in approximately n operations, thanks to its use of quantum superposition and interference. This algorithm has significant implications for AI, particularly in optimizing search-related tasks such as database lookups and pattern matching. By reducing the number of operations needed, Grover's algorithm enhances the efficiency and speed of AI applications that rely on extensive data searches, making it a crucial tool in the quantum computing toolbox. In the realm of AI, Grover's algorithm can be employed to improve optimization tasks, which are central to machine learning models. For instance, it can accelerate the training of AI models by optimizing hyperparameters more efficiently. This reduction in processing time can lead to quicker iterations and improvements in model accuracy. Additionally, Grover's algorithm can enhance search operations within AI systems, making them faster and more effective. This capability is especially beneficial for AI applications that require large-scale data processing, such as natural language processing and image recognition, where rapid data retrieval and processing are critical. Shor's algorithm is renowned for its ability to factorize large integers exponentially faster than the best-known classical algorithms. Traditionally, factorizing a large number is computationally intensive, but Shor's algorithm can solve this problem in polynomial time. This breakthrough has profound implications for cryptography, as many encryption systems rely on the difficulty of factorization for security. In the context of AI, Shor's algorithm can be applied to tasks that benefit from speedier number theoretical computations. The algorithm's efficiency can enhance AI's ability to model complex systems and solve problems that involve large datasets with underlying mathematical structures. The impact of Shor's algorithm on cryptography is profound. Its ability to factorize large numbers efficiently poses a threat to many cryptographic systems that underpin current digital security, such as RSA encryption. As quantum computers become more advanced, the potential for them to break these systems increases, prompting a shift towards quantum-safe encryption methods. For AI, this means re-evaluating security protocols to ensure data integrity and confidentiality in AI applications. Future-proofing AI systems against quantum threats involves adopting quantum-resistant algorithms and techniques, ensuring that AI remains secure in a quantum-empowered world. Quantum algorithms like Grover's and Shor's offer significant speed advantages over classical algorithms, especially for specific AI tasks. The ability to perform computations more efficiently translates to faster processing and reduced resource consumption. This is particularly beneficial in AI applications that require intensive data analysis and pattern recognition, such as fraud detection, real-time language translation, and large-scale simulations. By leveraging quantum speedup, AI systems can handle more complex tasks with greater agility, pushing the boundaries of what is possible with current computational resources and expanding the horizon for AI innovation. Quantum-enhanced AI is not just theoretical, there are practical examples of its application across various industries. For instance, in finance, quantum algorithms are used to optimize investment portfolios and manage risk more effectively. In pharmaceuticals, they accelerate drug discovery by simulating molecular interactions at unprecedented speeds. Quantum-enhanced AI also plays a role in logistics, where it optimizes supply chain operations, reducing costs and improving efficiency. These examples highlight the transformative potential of quantum algorithms in enhancing AI's capabilities, offering tangible benefits that drive innovation and competitive advantage in the marketplace. Despite the promise of quantum algorithms, implementing them is fraught with challenges. Technical obstacles such as scalability and error rates pose significant hurdles. Quantum hardware is still in its nascent stages, with current systems facing limitations in coherence time and qubit fidelity. Additionally, integrating quantum and classical systems requires overcoming compatibility issues and developing efficient hybrid algorithms. These challenges necessitate continued research and development to realize the full potential of quantum computing and AI. As the technology matures, overcoming these obstacles will be crucial to harnessing the power of quantum algorithms for practical AI applications. In conclusion, quantum algorithms like Grover's and Shor's are poised to revolutionize AI by providing significant computational speedups and enhancing efficiency in various tasks. As we continue to explore and refine these technologies, their potential to transform industries and advance AI capabilities is immense. Ongoing research and development will be key to overcoming current challenges and unlocking the full potential of quantum-enhanced AI. We encourage learners to stay informed and engaged with these developments, as understanding quantum algorithms will be increasingly important in navigating the future landscape of AI.